27 on the most recent homework.
Do you know what that is, or?
No, I don't.
Okay.
I know, but I was very confused.
Okay.
So,
And any idea what page we're on?
I think it's around 88,
98, give or take.
maybe 92. I don't know.
So is it, so it must be on maybe 95, so 27, does it sound like? So let capital H of T be the thermometer reading, does that sound about right? So on 27, we have H of T is going to be the thermometer reading in Celsius of a person T hours after the onset of an illness. Normal body temperature is 37 degrees in Celsius. Find the formula for the fever. The number F of T of degrees greater than normal after T hours. So H of T is going to be our temperature. 37 degrees is normal, I guess, in degrees Celsius. So we want a formula for the fever where F of T is degrees greater than normal. So we will say H is going to be, and what I call F of T. And so degrees greater than normal is going to be then what we measure that to be. Let's see. Oh, good question. The T is standing for after T hours. Normal body temp. What's that?
37 minutes T.
Let's see. Person. So H of T is the thermometer reading. So I think what we want, and we want F of T to be the degrees greater than normal. So what I think we want to do is measure our temperature, and I think we're going to call that capital H of T. And then subtract the 37 to see how much greater than normal that is. You have to kind of sort your way through all the words on this. Is that okay? Anything else from homework? Any homework? Okay. So I'm going to talk then about composition in inverse functions. And again, an idea that hopefully you've seen before, but we'll try to put some new twists on it and maybe go a little further with it. So this is section 2.5 in our book, composition and inverse functions. So I'm going to give you a couple of equations first. So we'll say f of x is going to be 3x minus 4, and g of x is going to be 5 minus x squared. So there's a couple of functions. So what we mean by composition is we can create a new function out of two old functions, and we can sometimes evaluate that just at a number. So we'll read that as f of g of 3. And so what that means is we're going to start with the number 3 for x. We're going to plug that into the function g first. We'll see whatever g does to that. And then we'll take that result and plug it in as an input value or as an x value into the function f. So it's going to kind of work its way inside out there. So we get g of 3. And there's our notation, and that's how we say that. G of 3 means we're going to plug 3 into the function g, plugging in the 3 for the x. So that's going to be 5 minus 3 squared. And that's going to be 5 minus 9, which is negative 4. So then that in turn becomes the input value or x value for f. So the 3 enters into g, g changes it, and then that changed value enters into f. And so then we're going to plug that in. So the negative 4 goes in for the x in the f function. And so we'll get negative 12 minus 4. So I believe that's going to be a negative 16. Okay. And in general, it's not commutative. So in general, what we get for f of g of 3 is going to be different if we switch the order, if we do g of f of 3. And so we can, and so let's just do that real quick. So we have g of f of 3. So this time the 3 first goes into f. And so f of 3 is going to be, I guess we get 3 times 3 minus 4. And so 9 minus 4 is going to be 5. We okay so far? I need nods of heads. Okay, and that in turn is going to go into g. So we're going to get g of 5. And so we'll take that 5 and throw it into g. So that's going to be 5 minus 5 squared. And so that'll be 5 minus 25. And so in general, as we can see, you don't get the same thing. You get different values. Now you can also write this. Notationally, this is probably what we see the vast majority of the time, but there is other symbolism too that means the same thing. So we could say, for example, f composed with g. So we write this kind of open circle there. F composed with g. And let's just say of x, because we can actually create a new function, not just evaluate it at a particular number, but we can actually create a new function out of these two old functions. So my students all know this is read as f composed with g of x. Mr. Hogstead's students sometimes call that fog of x. It's one way you can tell the difference between my students and his. I'm just kidding. So this means the same thing as f of g of x. So f composed with g of x means that. And so in this case, what we're going to do is we're going to plug the entire function g of x as an input value into f. So that entire 5 minus x squared is going to go into f in place of x. Does that make sense? Okay, so tell me what to write down. This is going to be
3
good.
parentheses 5 minus x squared and parentheses minus 4.
Very good. And then we'll just simplify and clean that up a little bit. So I guess distributing that 3, we'll get 15, and then minus 3x squared. And was that a minus 4 if I can read my own writing? And so that's going to become. So what we can see we have with this f of g of x, or if we use this notation meaning the same thing, f composed with g of x, is we've taken two old functions and combined them into a new function. So you can create new functions out of old. You can also do, I mean, it seems weird, but you can do f of say, let's say 5. So you can compose a function with itself, weirdly enough. And so in this case, we could take 5. So first we plug 5 into the function f in place of x. And so that'll be the 3 times 5 minus 4. 15 minus 4 will get 11. And then we turn around and plug it right back into f again. And so this time we'll plug the 11 in for the x. And this is perfectly well defined. So this time we'll get 3 times 11 minus the 4. And that's going to be
33 minus 4.
33 minus 4, and that's going to be 29. Very nice. Okay? So let's go back to the composition with functions and see if you can do that. So I'm going to give you g composed with f of x and give that a shot. Remember, we don't distribute that exponent. When you plug it in there for x squared, you're going to have to either multiply that out and then distribute the negative sign using the right order of operations, or if you remember our shortcut, first one squared, twice the product, plus the second one squared, you can use that here as well. Okay, we all got into at least this part, 5 minus the quantity 3x minus 4 squared. So here's where, I mean, you're welcome to multiply that out, and you can do your box thing if that's the way you multiply polynomials. What I'm going to encourage you is to, because we will do so much of this squaring of binomials that I think it's a real time saver to just learn that shortcut. It's going to be the first term squared, and so the first term squared is going to be 3x quantity squared, which is going to actually be how much? 9x squared. So that's going to be a 9x squared. Now we're going to get twice the product, and we'll let the sign fall where it may. So the product is going to be 3x times negative 4. That much is going to be negative 12x. Twice that means times 2 is going to be, so that's going to be a negative 24x. And then this third term is always going to be plus because it's going to be squared. And so the negative 4 squared is going to be 16. Okay, so there we have it. And we can distribute that negative sign and combine anything that we can. So it looks like we can combine the negative 16 and the 5. I'm going to leave it as negative 9x squared plus 24x. And then negative 16 minus 5 is going to be...
Wouldn't it be plus 5?
Yep, did I say negative?
Yeah.
So how about a 5 and a negative 16? Does that sound better? It's going to combine to be negative 11. There we go. Okay?
Wait, is the 24 also negative?
It was negative when we squared it,
Okay.
but then that minus has to distribute over everything inside there. So it's going to switch that negative to a positive. Is that okay?
Mhm.
All right? Okay, so I'm going to give you now, instead of giving functions as equations, I'm going to give you functions, we say numerically, that is as a table of value, and we're still going to do this composition stuff. So what's f of g of, what's g of f of, what's f of, maybe g of g of. So here is going to be our function f. So we're going to get this table, and we're going to say the x values here are negative 2, 1, 4, and 7, and the f values are going to be 3, negative 2, 6, and 0, and then the g values, so our function g of x, also is going to be given numerically, and it's going to have negative 2, 4, and 6 as x values, and 3, 7, and negative 2 as its functional values, as its y values. And then I'm going to ask you, what is f of g of 4? You find f of g of 4. I'll give you a moment there to track that through. So hopefully we can see that the g of 4, we go to the function g, here's the input value, x is 4, we read off the output value 7, and so this becomes f of 7. And then 7 becomes the input value, so we run over the function f, using 7, plugging it in, we're going to get 0. You okay with that? Okay. How about g of, say, 6, g of 6. So the g of 6 is going to give us negative 2, and then g of negative 2 is going to be 3. Okay, looks like we're okay with this. Okay, so let's do that. Let's talk about inverse functions. So something you did also in the past, hopefully. So for inverse functions, if we say f of x is going to be 3 minus 5x. And let's see what we can do. Can we find f inverse of x? Do we know how to do that? And remember, the notation is going to look like this. So that is not a negative 1 exponent. That's an inverse function notation. Unfortunate that they look exactly the same. But in context, this is not 1 over f of x. So how are we going to find it?
You're gonna switch the x's and y's and then solve for y.
So we need to have me walk through it, or can you do it? Anybody want to see it done? Okay, go ahead and give it a shot. You can jump on, and I'll give you a head start, and then I'll jump in case somebody wants to see how we're doing it or compare what you're doing with the way to do this. So ignore me if you know what you're doing. So I'm going to replace the f of x by y first, so I just changed the notation there. I haven't really done anything else. And we can switch the x and y. And we will solve for the y where it falls down. So there's lots of correct versions of this, and I don't care which one you use. So probably most of us, because it's just the quickest, easiest way. Did you get 2x minus 3 over negative 5? Okay, and that's fine. You can stop there, and I'm totally okay with that. If you don't like that negative 5 in the denominator like that, we can multiply top and bottom by negative 1. That'll make the x negative and the negative 3 positive. And if I write the positive 1 first. So aesthetically, this might look nicer, 3 minus x over 5, but they're equally acceptable. And if you don't like it as one big fraction, you could write it, split it up and call it 3/5, and then a minus 1/5 x, and look at that more like y equals mx plus b. Any of those is acceptable. You don't feel you have to get to one in particular. Okay, so there's our inverse. Now we'll talk about the graph because this has significance with inverses. So I'm going to actually graph both the original and the inverse. So I'm going to graph the original. I think I'll do it in yellow here. So here's going to be our f of x. And we can see we've got y-intercept of 3 and a slope of, and I'm going to label that point 0, negative 3. And then the slope is going to be a negative 5. So I'm going to go down 5, 1, 2, 3, 4, 5, and over 1. And that point, it looks to me, is going to be 1, negative 2. And that is going to be our function. So that is our y equals f of x, our original function. Now for the next one, kind of a nice way to graph things is if we know these ordered pairs, what's true about a function and its inverse is they switch the role of x and y. So if this is a point 0, negative 3 on the original function. Say it again. Ah, thank you. That's going to make a difference. Otherwise, this isn't going to look right at all, and then I'd really be struggling. How about 0, 3? Does that look better? Is this one okay? 1, negative 2? Okay. So if we switch this, we'll get 3, 0. That has to be a point on the inverse. So I'm going to plot that point 3, 0. You with me there? And similarly, we have the point 1, negative 2. So if we switch that, it's going to be a negative 2, 1. That must be a point on the inverse. If we connect those, because we know that the inverse in this case is also linear, we could kind of see it down here where it looks like y equals mx plus b. You can tell it here because you just have x to the first, not a higher power of x. And so this is then our inverse function in the purple. And so the idea is with the graph of any function and its inverse, if you look at that line y equals x, that line that goes through the origin at a 45-degree angle, has y-intercept 0, slope 1, those all mean the same thing. If you take the original, say the yellow, and you reflect it in the line, in that dotted line, the y equals x. That is, if you imagine writing this in very wet ink or chalk, fold on the dotted line, the imprint should be the inverse. Okay, that's what that means. And a point where these are in common, where these intersect each other, the original function and its inverse, that must lie on the line y equals x. So that's going to be a point where they have the same x and y coordinates. Does that make sense? Okay. So what we want now to do is we're going to, okay, if I erase this now, we're done with that. So still talking about an inverse here, and I want to still save those for a moment. So I'm going to leave that version of our inverse right here. I think I'm going to like that better. So the actual definition of an inverse, so f and g are inverses of each other. So two functions, f and g, are inverses of each other if and only if. So this is not a Mr. Street made-up abbreviation, the IFF. This means if and only if. So I'll talk about this in a minute. It goes both ways. If and only if f of g of x is equal to x and g of f of x is also equal to x. Which seems weird. Let's see what that means. So, and this is the definition. So what that's saying is that if f and g are inverses, then this relationship must hold. That f and g of x, they undo each other, and they just give you right back to the x, in whichever order we do it. If this holds true, so the if and only if means it goes the other way. If we find two functions that do this to each other, then they are, in fact, what we call inverses. So what I'm going to ask you to do next, are we okay so far on that? I mean, it looks like weird, but we'll see how it plays out. So I will ask you sometimes to verify that f of x equals 3 minus 5x and f inverse of x, which we're calling f inverse of x. And I'm going to go back with the way we originally got it because I'm imagining that's probably the version that most of you came up with on your own. And f inverse of x are in fact inverses. So if you are asked to verify, that's like a proof. That means prove that these two functions really are inverses. So if I had not given you this already, or maybe I just called this g of x, and I said verify that these two are inverses of each other, it would not be okay to take this one, switch the x and y solvent, come up with this and say, see there, it must be the inverse. Because that's not really a mathematical proof. The proof has to go back to the definition. You have to show that these two functions really do satisfy the definition of what it means to be an inverse. And what you have to do when it asks you to verify that they're inverses is you have to show both of these things. That f of g of x is equal to x and that g of f of x is equal to x. Okay? I'm going to rewrite this up here so I can have that space. So I'm going to say we're claiming that f inverse of x is x minus 3 over negative 5. So then what the verification is actually going to look like is we're going to start with something like this. So we're going to show f of f inverse of x. Okay, and then we're going to see what that's actually equal to, and we're going to work it out step by step, and hopefully at the end we're going to get just x. So if we can get that that is x, we're halfway home, because then we have to come back and do it this way also. You with me? So that means I'm going to take f of, well now I'm going to plug in the inverse, what we have called the inverse. So that's going to be that x minus 3 over negative 5. You with me? Okay, so then that's going to look like, now we'll plug all this stuff, this x minus 3 over negative 5 is going into the function f in place of x. Okay, so that's going to look like 3 minus 5 times, and now here comes our x minus 3 all over negative 5. We okay so far? Now, we got to go step by step. So this negative 5 times that negative 5 there, they can cancel. So this is going to become now 3. The negatives cancel, so that's going to be plus. Right, we're canceling those. And so we're going to get just the x minus 3. Okay to there? And now we can let the 3 and the negative 3 cancel each other out. and we're halfway home. We've shown that f of f inverse of x is indeed equal to x. Now, when you do this on, say, a test, don't leave off this part, because if you don't tell me which is which, I think you don't know. And so that'll cost you a point. So you must show that first step. Okay, so help me do the next one. So now what else do we have to show? So we're halfway finished. Now we're going to have to do what?
F inverse of f of x.
Nice, f inverse of f of x. Okay, and that's going to look like f inverse of
3 minus 5x.
3 minus 5x. Throwing in that f of x. Okay? And so now, let's see, f inverse is over here. That's at x minus 3 over negative 5. So this is going to be waiting for direction here.
3 minus 5x in parentheses, and then minus 3,
Okay, and I don't even really have to have the parentheses there. I think we're okay that way.
and then over negative 5.
We all right to there? Okay, now we can let the 3 and the negative 3 kill each other off. So that takes us to negative 5x over negative 5. Now we're cleared to cancel the negative 5. And so we're going to get x. And so we have shown that f inverse of f of x is indeed equal to x. Therefore, they're going to be inverses. Okay. All right so far? So let's switch to some words. Now we're going to give our function, we would say, verbally. And I'm going to ask you some here. This can get a little tricky on the inverse, especially figuring out exactly the meaning of it. So I'm going to say, if y is equal to f of t, where y is the population of birds in thousands, population of birds in thousands, t years after 2007. So now we have established what the meaning of the y is, and also what the meaning of the t is. Okay, then what I'm going to ask you is interpret the meaning. So interpret the meaning, and I want correct units here. So use correct units. So first, I want to know what does f of, say, 5 equal to 400 represent? Use correct units there. And you can discuss that with somebody next to you. So you can turn to somebody and say, what do you think?
Population is 400,000.
Did you say 400,000?
Emma, what did you think?
5 years after 2007, there's 400,000 birds.
Very good. And so you can say 5 years after 2007, or you could say in 2012, there are 400,000 birds. Good. So let's do something different. Okay. Can you interpret the meaning of that? F inverse of 300 is equal to 8. This is where it gets a little harder, I think. And you can turn to your neighbor when you think you have an idea here and see if you can formulate a coherent sentence to say what this means.
Well, I think it,
200,000 birds in 2015.
yeah, but like, I guess it's kind of implying that what the year is 2015 because there are 3,000 birds, 300,000 birds.
Could be that
I guess it's like the independent and dependent are switched.
Yeah, so you're going to start with the input there, yeah. And that's the hard part, I think, sometimes to phrase the sentence. So, Nora, did you want to try that? I thought,
There were 300,000 birds in 2015.
okay. So what does it appear is happening to the population of birds here? Increasing or decreasing?
Decreasing.
At least it was that in that 1 year, yeah. So the population of birds reaches 300,000 8 years after 2000, what did I say, 7, so in 2015. Okay, good. So these can be tough. The inverse is one that we struggle with even in AP calculus, I think. So let's go back to our temperature cricket here, our thermometer cricket. So we have T is equal to 1/4 R plus 40. And hopefully that's kind of familiar. T is going to be our temperature in degrees Fahrenheit. And the R is going to be our chirps per minute. This is tough because now we have a rate in there as well, the chirps per minute. And so can we interpret here? So again, trying to figure out how can we understand the meaning in words here. So interpret, first of all, T of 100 is equal to 65, and then see if you can say T inverse of 60 is equal to 80, and put the words using the correct units into those two statements. So the way we're writing T as a function of R here, even though I think in real life that might be a bit of a stretch, but we're saying the temperature here depends on the chirps per minute. Like those crickets are controlling our temperature here. I wish they would hurry up and start chirping a little quicker. Could use a little bit of warmth. Ashlyn, want to take a shot at the first one? What does that mean?
When the temperature is 100 degrees Fahrenheit, there are 65 chirps per minute.
I think here, though, what we actually have is, this is T of R. So our input value here is going to be actually the chirps per minute.
So 100 chirps per minute, and temperature 65 degrees.
There you go. That's not what you said the first time, was it? No. Okay, yeah. So it's kind of, yeah, and it's kind of weird because of the way we made this function. So when the crickets are chirping at 100 chirps per minute, the temperature is going to be 65 degrees. So it's like the crickets are controlling our temperature somehow. Okay? Now the inverse, can you try that? You need a minute?
That one would be like what I said.
Yeah, exactly. So you want to try that one? So that's going to be,
With the temperature 60 degrees, there's 80 chirps per minute.
yeah, exactly. Good. Okay, so suppose, different question here, not related to this at all. So suppose we know only two things about some function g, that g of 10 is equal to negative 26, and we also know that g inverse of 0 is 7. So if we know that, if we know the value of g at one point and the value of g inverse at a different point, what other values do we know about g and g inverse? What other values do you know about either g or g inverse? Understand what I'm asking here? Yeah. Well, let me give you a minute to think, because I'm not sure if everybody does, but Nora's on it. Okay. So hopefully you know two other values, if you can figure out what this means. Is that hard? Yes or no? No, you got it? Okay. So one of those values, Nora, that you know is going to be what?
G of 7 and 0.
Good. So if 0, 7 is going to be an ordered pair for G inverse, then G is going to be able to switch those around. So if the input value for G inverse is 0 and the output is 7, then an input value of 7 for the original function G must give us an output value of 0. They get switched. Is that making sense? Okay, so a second, Ariana, what's another thing then that we know? Putting you on the spot here. Do you know anything from here? Okay, so can you say it in, no, yeah, you're right. So can we say it in notation like we did here? So here we knew G inverse of 0 is 7, so we said G of 7 is 0. So G inverse of? Nice. Okay, so we know we can switch those. Okay, it's going to be quick. Going to do a quick tough inverse here. We have a moment. So can you, or not tough inverse, tough domain. So that's tough domain. So going back to some old stuff. Find the domain, and you're on the clock here. F of x is equal to the square root of, and we will say 81 minus x squared. Find the domain of that. You know how to start? Let me pick on somebody. Gage, how are we going to start this thing?
I'm honestly not entirely sure.
Okay, who can give us a hand?
So you would just make it 81 minus x squared, and then you would make it, in parentheses, 9 minus x times.
Okay, what do I need to put here? You're on the right track, exactly. What am I going to put here? Everybody help us out. What do we need here?
Equal to 0.
Greater than or equal to 0. Okay, yeah. So whatever's inside the radical has to be non-negative, has to be positive or 0. Okay, then because it's an x squared, we can't just add the x squared and square root both sides. So you're going to say we have to put the parentheses in, which I love. That's exactly right. So we're going to factor that thing. And do you know how it factors?
Yeah, so 9 minus x and 9 plus x.
Oh, very good. And some people don't like this, so some people might first factor the negative out and call that x squared minus 81, and then they would be more comfortable calling that x minus 9x plus 9. Either way is okay. So either what we have in white or we have in the blue, you're going to get to the same place as long as we keep doing it right. Okay, now you must show a number line. Okay, keep going. You're on a roll here, Ben. What next?
So then you would put 0, I think. Right?
Actually, what's going to make this equal to 0?
The
9, and also,
negative 9.
okay, so that's what's going to go on here is what's going to make this 0. And those are going to go as solid dots. Excellent. Okay? Now what?
Try points.
Yeah, we're going to test each of those 3 regions. So what's a good representative from the far left region? Negative 10 works. 9 minus negative 10 is? 9 minus negative 10 is actually going to be positive or negative? Positive. How about 9 plus negative 10? Negative. Multiply positive and negative, we get, is that greater than or equal to 0? That's negative, less than, so no domain out here. Represented from the middle region. 0 is a good choice. 9 minus 0 is positive or negative? 9 plus 0, product of a positive and a positive. There's our domain. right in there, and we can check the far right region, say 10. 9 minus 10 is going to be negative, times positive, no domain there. So our domain is going to be, how do you write that?
X is less than or equal to -9.
And at the same time,
X is less than or equal to positive 9.
greater than or equal to. So we can write this as a double inequality. Very nice, very nice. Remember, test on Friday again. I gotta get you a time. I'll let you know as soon as I can. If you don't like your test, you need to get in and see me after school as soon as you can, and we'll get the ball rolling. If you haven't taken the test yet, hurry up. Come in and see me. You gotta get that going.